Today we have a guest speaker, Nick Lee from NVIDIA. So Nick is a developer technology engineer, and he kindly agreed to talk about scientific visualization on NVIDIA GPUs. Nick has a background in scientific visualization, both on a desktop and in HPC, with a focus on interactive real-time analysis of large data sets on GPUs. And today, Nick will talk about three really interesting technologies developed at NVIDIA: OptiX, Index, and Omniverse. And on this note, I will pass the microphone to Nick.
All right, thank you, Alex. So Alex mentioned my role at NVIDIA is developer technology engineer, which is a phrase I wasn't familiar with before I started NVIDIA. And essentially, it's just it's a role that's on the engineering side, but I also tend to be a little bit more outward facing. So this involves being a Viz practitioner in setting together some of the demos that we present at various conferences, but also helping working directly with scientists and practitioners to help them use NVIDIA GPUs for visualization. So just a quick look at what I'll be talking about. I want to start with an overview, kind of a high level look at what we're doing at NVIDIA with regards to visualization. And then I want to delve into ParaView specifically and how to use the OptiX ray tracing backend and the Index volume rendering plugin in ParaView. And then finally, I want to talk about Omniverse a little bit, what Omniverse actually is, the underlying technology that we rely on called USD, which is just a scene format. And then for both the ParaView and Omniverse sections, I want to give a little overview, like a demo, on how you can actually use them in practice. So this slide just summarizes some of the activities that we work with at some of the activities that we've done at NVIDIA. So you can see a bunch of different visualization examples. On the upper right and lower right are kind of more traditional visualizations. So the upper right would be a astrophysics data set, and that's volume rendered. And so that would be accelerated using Index. On the lower right is a SpecFem 3D simulation. So that's like a reconstruction of the Earth's mantle, and that's rendered using path tracing using OptiX. But beyond the typical standard, what you usually think of as scientific visualizations, those technologies can be used for a lot more. So in the top center is a database visualization where we took a general database, we computed a clustering on it, and then we put that 3D clustering into ParaView, and we're using the OptiX path tracing backend to give us realistic lighting, and that helps illuminate the shape of that cluster a little bit better, and it can help improve perception. The underlying mathematics of path tracing are really just about light transport, and it ultimately comes down to computing fast intersections of rays and geometry. That's really useful for rendering, and we have to shoot a massive number of rays for rendering, but that's also really useful for a few other simulation capabilities. So on the upper left is an example of like a LiDAR sensor data set. We're rendering that here, but we could also do simulation of LiDAR, and that's really useful for applications like robotics or automotive type applications. But you can also do the same thing for sound transport if you want to compute acoustics, or we're collaborating with the IceCube experiment at the South Pole to help them compute light transport in their 1 kilometer cube ice detector. So just to give context for how I think about visualization, I usually think about it in kind of two contexts: discovery and analysis, which is more your day-to-day visualization. That's something you'll do for a specialized audience, yourself or colleagues, people who know most of the context you need to talk about, and you really just need to get some particular point of data or some new discovery across. It's meant to be fast, both in terms of rendering time, you don't want to sit around and wait for it, but also in terms of scientists or Viz practitioner time. You're not going to spend a huge amount of time getting this visualization perfect. It just needs to be quick enough and accurate enough to get the idea across. And this is usually handled by tools like ParaView or Visit, or maybe even MATLAB, or maybe even just in Jupyter notebooks. On the other hand, is much more of a presentation and publishing kind of scenario. So this would be for a broad audience. And what you might want to try to achieve is something like cinematic visualization. So this would include advanced lighting and advanced effects like depth of field or motion blur. Because you're doing this a lot less frequently, and because you're doing it for a much broader audience, you're willing to spend a little extra time on it, both in time to configure it and get the visualization set up, as well in time to actually render it. So you're willing to spend some more core hours to get really nice looking frames out of it. You can use some of the tools that are, I've categorized on the left, like ParaView and Visit, to create presentation quality graphics. But you may also want to use tools that are typically reserved for more film type rendering, like Maya and Houdini and Blender. So I've kind of created this dichotomy, but it's a little bit of a false dichotomy, because what we really like to do as NVIDIA is bring these closer together. That involves both making the rendering in the traditional discovery and analysis tools better and higher quality and more cinematic. But it also involves making these presentation tools much easier to use, so that even scientists can jump in with a film quality tool and get something without having to spend weeks or months learning how to use those tools. Beyond just presentation, we think that high quality rendering is useful for discovery as well. So to give a quick example, this is the same SpecFem 3D dataset that's rendered in ParaView using both the traditional OpenGL or software renderer, as well as the OptiX path tracer. So on the left is the traditional one. You see it's missing a lot of shadows, a lot of highlighting compared to the right image. So not sure if you're able to see my mouse, but towards the upper right of the data set, there's like a ridge next to kind of a cave. That ridge is pretty much invisible on the left-hand side. So right around there, if you can see my mouse. In the lower left of the image, or really anywhere that there's a deeper cave in this data set, it's really hard to see that in the left image. It's hard to see how these layers relate to each other. If you're working with ParaView, you could maybe move the image around and get some parallax to help you understand the geometry of it, but that doesn't come across very well in a still image. So that's one way that you can use these high-end rendering and lighting effects to not just create a nicer looking picture, but also to help improve the perceptibility of your data. So as a quick example, I want to show a video that we did pretty recently. So this was from last fall. This is a data set we got from the Gordon Bell winners at Supercomputing 2020. And this is a COVID viron simulation. So as we zoomed in here, you saw the lipid layer of a lung cell as well as the ACE2 binding site. And then we're kind of traveling up a spike protein of a COVID virus right now. And now you can see the lipid layer of the COVID virus. This whole data set is, if I recall correctly, like a couple billion particles. And the rendering we did kind of matches a typical visual metaphor that people are used to seeing for molecular simulations for biology data. It's this sort of, each atom is one little ball and then that forms molecules. It speaks to a language that people are already familiar with. So this is an excellent tool for outreach. In order to render this, what we did is we loaded this into an existing viz package called VMD that we used to ingest the data and export it in a form that we could load into another tool called Omniverse Create. We also use Blender to help us design the camera path that you're seeing here. And then when we got that all exported, we got that looking how we wanted. In Omniverse Create, we were able to add some of the final effects like motion blur and a little depth of field. And this is all path traced and that kind of thing. Even though this is a pretty large data set, using Omniverse Create and using very fast ray tracing hardware we were able to view this data set in real time, get our animation and all of our visualizations set up and looking exactly how we want it, and then finally like render out the final frames. And all of that took a pretty reasonable amount of time. I don't think we had this data set in our hands for more than 2 weeks before we produced the final video. So moving on to how you can actually access these technologies. The first thing I want to touch on real quick before I dive more in depth into ParaView is some of the work we've done to enable visualization in Jupyter. So this is kind of towards both improving the quality of presentation or typical discovery and analysis tools, and bringing those presentation type tools closer to the user, closer to where the scientist is actually working. So the little animation I'm showing on the left is a project called ParaView. It's a widget so that you can work with ParaView directly in a Jupyter notebook. So you can see as I'm running through steps on the left here, you can see I pop up a little widget window, and that's using ParaView directly with the OptiX backend. So you can see I can adjust the lighting in real time, and I'm getting kind of a nicely illuminated, physically based rendered skull. I include some links here. They're probably easier to access from the slides I shared. The links cover both ParaView, an introduction section to ParaView that I did for GTC last year. I also include some links to a project called Node Rapids, which is a project to add GPU acceleration to JavaScript rendering. That's kind of an exciting project. It's still a little bit newer, but if you're interested and you do a lot of JavaScript notebook-based rendering and you'd like to accelerate that and you'd like to make that a little bit faster, it's worth checking out the session that I linked. So diving into ParaView a little bit, I'm kind of assuming most of the audience is familiar, so I'll skip over a lot of this. But ParaView, as we all know and love, is an open source BTK-based data analysis and visualization tool. A lot of the things it does are uncommon for film quality tools. So say doing distributed processing and rendering is something you're unlikely to find in tools like Maya and Houdini, or at least a little less commonly. It also has a huge number of readers for scientific file formats that are often very domain specific, as well as some of the tools that we're used to using like isosurfaces and streamlines to go from some form of raw data to a visual representation. Native ParaView supports both software and hardware accelerated rendering. You can just use the OpenGL backend, and you can get very good images out of it if you design it that way. But we wanted to take it to the next level. So we worked with Kitware to add some of our technologies into ParaView directly. So on the left is an example of an image using the OptiX path tracing backend. And that gives us the sort of high-end lighting that can help illuminate really complex geometry. So in that streamlined case, you can see a lot more detail than if that were just flat shaded. On the right is an example of ParaView running with the Index volume rendering plugin. So Index is a library. I should explain, sorry, a little bit more about OptiX. OptiX is an API for ray tracing. So it's very low level. And unless you need to do like simulation with it, or you're trying to do a special case scenario, it's easiest to access via the like ParaView backend or something that's built on top of OptiX. Index is a library that's still easiest to access via, say, ParaView, but it does a little bit more, so it's not quite as low level. But you can use it directly in ParaView to do the sort of standard volume rendering that you might be used to. Index is very fast. It provides very, very high quality, and it also is works in distributed mode. So I'd like to jump in with a demo quick, just to show you how to use, I'll start off with showing you how to use the Index plugin. So first things first, this is a standard ParaView. I'm going to go up to Tools, Plugins. If you use the ParaView plugins, you probably already know this part, but if you're running in client server, you'll have remote and local plugins. You'll have to enable them both. I'm just running locally in this case, so I'll just enable index locally. So once that's enabled, I want to pull in my volume data set. And I have some metadata that I need to set to let ParaView know what the structure of my data is. Oops. All right, and then to actually volume render it, I just have to go and set the representation to NVIDIA index. And I cheated a little bit. I messed with the transfer function ahead of time and just set up a really simple transfer function. But you can see that this runs interactively pretty well. This isn't the biggest data set. It's only 432 cube voxels, but it's pretty fast. Index on this GPU on a workstation, I expect I'd be able to handle at least 1K cube voxels without any issues, and probably running at a similar frame rate. So moving on, I want to talk about the OptiX backend a little bit now. So for the OptiX backend, I'm going to have to do a little bit more setup. I'm going to use the same data set that I just showed in that image. So to start with, it's just a vector streamlined turbulence data set. So to start off, I want to load in my data and then set up a source of seeds for my streamline. So this will just take me a minute to get going here. And my ultimate goal for setting up my streamline source here is to create a ring and just spawn streamlines around the outer edge of that ring. So I've got a ring set up and I just want to add a transform filter here to get it aligned with my data. All right, let's double check that. I think I probably made a mistake in the calculator. Yes, I did. Just in case you were wondering whether this is a live demo, any mistakes I make should prove that. Okay, so that looks like the streamline seed source that I want. So I can go ahead and add a stream tracer. And I'll select my vector data set as my input and that transform I made as my seed source. And I only want to integrate forward in this case. And I'll wait a second for that to integrate. Okay, and there we go. Maybe I'll pick a slightly different color scale in this case. Okay, so that gives you some streamlines. The color table the color table I selected gives you some ability to discern different parts of the streamline data set. The color is just velocity magnitude in this case, but it's still pretty complex. There's a lot of overlap, especially in the center region where things start getting really turbulent here. So we might want to try to apply ray tracing. As a first step, ray tracing doesn't work terribly well with line or point data just because it's then trying to compute intersections of infinitesimal objects. So I'm going to apply a tube filter to give a little bit more heft to those streamlines. Okay. So in order to actually turn on OptiX, the OptiX backend is built into a standard build of ParaView 5.9, which this is. This happens to be the desktop build. I don't recall off the top of my head whether the OptiX backend is built into the EGL headless version of it. I would have to double check that. But since OptiX is already enabled, I can just go down to the bottom of the properties window and go to ray trace rendering and enable it. And that will take a second, assuming it doesn't crash on me. And then I can switch the back end from Osprey to OptiX. So you can see that actually runs pretty quick. In its default state, it is a little bit noisy though. And that's because it's doing a lot of randomized sampling. So you get pretty high variation of lighting between pixels. We can smooth out a bit of that noise by doing more samples per pixel. And one quirk of the OptiX path tracer is that if you set it to samples per pixel to at least 4, denoising becomes available, and denoising will help smooth out some of that, some of those speckles that you see where you're getting kind of bad sampling. So this is already looking pretty decent. You can still see, and it might not show up in video very well, you can still see a little bit of noise in certain parts of the data set. So in that case, you can add more progressive passes. And this will cause ParaView to just continue, when you let the still image sit for a little bit, it will continue running ray tracing and continue to converge samples until you get a more stable image. So there's a lot more that you can do with ray tracing and path tracing directly in ParaView. So I could add some more geometry. I could set up different materials for certain objects. I won't go into the whole thing. There are some resources that you could look at online that should give a more complete tutorial.
Nick, there is a question in the chat from Kumar. And the question is, would it be possible to use the NVIDIA index backend instead of OpenGL with VTK in ParaView? So
the index backend is specific to volume rendering. So it would run instead of OpenGL, or actually if ParaView is rendering combined volume and geometry, I believe that will run in conjunction with OpenGL. So it will use OpenGL in parts and then index for the volumetric parts. For OptiX, OptiX is a replacement of the OpenGL backend. So that instead, it doesn't do any OpenGL, and instead will render images just using ray tracing by OptiX. Okay, and that was an excellent point for a question too, because next I want to move on to talking a bit more about Omniverse. So Omniverse is still a fairly new technology. We announced it a couple of years ago, and it just went into open beta at the beginning of this year. Omniverse arose from a common problem that we noticed a lot of our customers having. So our customers would be using all these different tools to try and work together and collaborate. So one customer might be using, or even customers, people working within the same teams might be using a combination of Maya or 3ds Max or Unreal Engine or Unity. And then into this same mix that already is complex, this really complicated ecosystem, we wanted ParaView to be able to also work with all of these tools. So you can see that if you start making these tools interoperable, if you have to do that on a pairwise basis, that problem becomes exponential very quickly. The burden to maintain all of that interoperability is kind of impossible, and it only grows over time. So instead, you just need a way for all of these tools to talk to each other natively in the same language. We looked around and we found USD to be the best option for that. USD is the Universal Scene Description. It's an open format created by Pixar. It was originally created for their own use to describe scenes in their own movies, which if you've seen a recent Pixar scenes, you can tell that those data sets are probably massive at this point. So USD is designed to be able to handle massive data and to describe how all of this data should interrelate to each other. So you can describe meshes, you can also describe materials. It does have some initial support for volumes as well. And then NVIDIA has further extended it to add some of our own useful capabilities. The quote that I use a lot is, and that gets used a lot around NVIDIA, is USD is the HTML of 3D worlds. Every application should be able to talk USD, and every application that can talk USD can interoperate with each other. USD is a great start, and all of these tools can already work together just by being able to export and import USD. But we wanted to go another step further. Even if all of these tools can talk to each other, that still leaves users managing shared files, shared file systems, file versioning. All of that turns into kind of a pain, and it ends up with people emailing links or sending links via Slack and having to do their own uploading. Instead, what you'd really like is a live synchronized database that all of these applications can connect to at the same time, and that users can edit online, and everybody can see each other's edits and collaborate on the same data at the same time. And that's the core, kind of the heart of the original Omniverse idea, was to provide that capability so that all of these applications can talk to each other. That core is called the Nucleus server. And we have added a ParaView connector that I forget whether we've officially released it, but if not, it's going to be released very, very soon. And that ParaView connector lets ParaView export data directly to a Nucleus server from where you can access it from Omniverse applications, well, any other Omniverse connected application. So to give you a bit more of an idea of why you might want to get your data into Omniverse and what that gets you. Omniverse at its core, it's of course Nucleus, which is in this box here. And it also encompasses all of the connectors that either we or other companies have written for their own software that let it connect to Nucleus. But beyond that, Omniverse has a ton of other capabilities. So a lot earlier in the talk, I mentioned Omniverse Create, which is what we use to do that COVID Viron visualization. Omniverse Create is based on the underlying Kit SDK, which includes a very high-end renderer. It includes physics simulation. It includes a lot of tools for editing and creating visualizations. Originally, this is designed for film use, but rendering is rendering. All the tools that you use to render really beautiful looking films can be used to also render scientific data. So to give you an idea of how the ParaView connector for Omniverse actually works, it sounds like it's very Omniverse specific, but in reality, it's not. The ParaView connector just turns the renderable part of ParaView's data into USD. So in that streamline example I presented earlier, it wouldn't take the vector data and output that to USD. It would only take that final representation, the part you're actually rendering. So at the very end, when I ran that tube filter and created tube geometry, that's the part that would go into USD. Via the ParaView connector, you can, if you want, just output to disk. Once your data is on the local file system, you can load that in whatever application you want that can use USD. So you could use Houdini, you could use Maya, you could use applications from anyone, or you could use applications, NVIDIA applications like Omniverse Create to load up and render that data. Alternatively, you can also connect directly to an Omniverse Nucleus server. This would be particularly useful if, say, you want to do remote collaboration with a colleague. One colleague could work with the ParaView, figure out an initial pre-processing pipeline, get to a renderable set of geometry, and then output that geometry to Nucleus, while another user loads that same scene in in Omniverse Create, and then configures other geometry and lighting and maybe any other context rendering that you want to do. So this is ultimately a very, very good tool for creating cinematic visualizations. I think it could be used for daily analysis. I think we still have some work to do to make it easier so that people can use it for that. But it's in its current state even a fantastic tool for creating sorts of cinematic visualization that help you express your data to a much wider audience. One other thing I've been forgetting to touch on too is Omniverse Create is fully Python scriptable. USD has Python bindings. ParaView, a lot of you are already probably familiar with ParaView's Python bindings. So all of this stuff speaks within the same Python ecosystem as well. And that I think really increases its usability. So next up, I want to show a demo, if I can quit ParaView here, on how to use the connector. I'm just going to use, for simplicity, I'm just going to do a much simpler example. So just to show off the connector, I'm just going to run a wavelet source. But first thing, I want to make sure the connector plugin is enabled. And it looks like it's already set up. The steps that I'm not showing is you'd have to both make sure you have a ParaView installed locally, and then you'd have to get Omniverse. Once you have Omniverse, the first thing you would install is the Omniverse launcher. And then from the launcher, you can install the connector into whatever ParaView installation you already have. I'm running in Linux in this case, but this also works fine on Windows. I don't know off the top of my head whether we support Mac or not. But the installation process is fairly simple. I just happen to be running with a developer build that I had handy. So in order to set up something to actually look at, let me get a wavelet source here. So this is running a standard ParaView window, and then to run the connector, before I forget, I want to make sure I have my settings set up. So if I go to edit settings and then the Omniverse connector, I have, in this case, an Omniverse server already set up. And then I still have this set up to a location I was using for setting up my GTC presentation. But I could also just as easily output this to disk. So if you select output local, it'll automatically output the resulting USD to your local file system. And if you don't select it, it'll just go to whatever Omniverse server you have set up. So it's fairly easy to switch between the two based on your preference. So I just went to the plus, I'm creating a new layout, and then for this layout, I'm selecting the Omniverse connector. And then once I have the connector selected, I just have to make visible the parts that I want actually exported. Now that I've made this visible, this will show up in Omniverse if I load that data set. So I'm going to start up Omniverse Create. And because I do development on this stuff, naturally I'm running another developer build. But the more normal way to launch this would be from the Omniverse launcher. And I know I'm going through this kind of fast, and in order to get through everything I wanted to, I'm leaving out a lot of details, but I have some links at the end that I'll share that will give a much slower, much more relaxed view of this stuff. So if you want to start working with it, that's probably going to be an easier resource to get started and really dive in depth. So let's see if the data set that I just saved came through all right. Okay. So it looks like the data's there. I had a color set up in ParaView. So if you notice, there's a loading bar down at the lower right here. That's loading an associated material that was created from that color map from ParaView. So that just takes a second to compile that shader and get that material set up. In the meantime, I might as well set up a little bit of lighting. So because it's a physically based renderer, you end up having to set up lighting in order to not have it be so dark. Whereas with like normal OpenGL shading, it's a simpler form of shading, and they always assume a standard level of ambient lighting. So you can see I can change the lighting positions and everything in real time. If I want to, I can switch from the RTX real-time renderer, which tends to sacrifice a little bit of quality for very high speeds. I can instead switch to path trace mode, which will render much higher quality, but will take a little bit more time. It's not bad in this case. This is a pretty small data set. So let's try and look at something a little bit more interesting. So let's see if I can load up. I also did some experiments earlier where I was using that same tubes data set, the streamlined data set. So let's see if I can load that without issues. I think I saw an error message back there, so it might be giving me problems today. So despite that vector data set actually not being that large, the streamlines it generates create quite a bit of geometry. So I end up being kind of close to the limits of what my local workstation is capable here. So that might be where I'm running into trouble. It looks like I am. So let me switch to a video I have here just so I can talk about it. Mute that. Okay. So you can see here, oops. There we go. So this is where I'm running through the same steps that I would be if I were running this live. And I'm loading up that same tube data set. So in this case, when I load it up, the scale's a little wonky. So I end up having to expand it, scale it up a little bit, and make that more easy to work with. But as I do, then I rotate it, and I do a couple other steps. So if you're familiar with any sort of digital content creation tools like Blender, a lot of these tasks and the UI modalities end up being very similar. It's a little bit different than ParaView, so it maybe takes a little bit of getting used to and getting comfortable with setting all this stuff up. But overall, it's not too tough to at least get some initial images out and to start working with your data. So with that, I think I'll let this play. I'm getting kind of close to the end of the things that I really wanted to get through. Does anybody have any questions about Omniverse at this point? I know I went through things kind of quickly.
I have a question. So you mentioned that the ParaView connector for Omniverse is currently you're currently working on it. So it's not included into the usual precompiled build of ParaViews. Is that true?
So it's good question. It is not included in the usual precompile of ParaView. It's a plugin, so you can just install it. You can download a standard binary from ParaView and then just use from the Omniverse launcher, install the plugin into that local installation of ParaView.
But this plugin, do you need to compile it yourself? Because usually plugins comes as sources. At least that's my experience.
Oh man, I don't know actually off the top of my head. You don't have to do the effort of compiling it yourself. When you click install, it may compile itself as part of the install process, but all of that should be more or less opaque to the user. The user just has to worry about, locating ParaView and starting the install process. So they don't have to mess around with like compiling it themselves.
Okay.
Okay. So that was a very, very brief overview of Omniverse. There are a lot more things that Omniverse can do. It's a very full-featured suite of applications. And so here are a couple of links to, if you're interested in getting started, at least kind of learning more about Omniverse and seeing what it's capable of. There's a lot of stuff that I didn't even touch on, like a physics simulation. If I had wanted to, I could have enabled physics on that tube data set. I could have used it as a rigid body or collider, added some gravity to it. One example I know that people have looked at is they've looked at even using the game physics that are in Omniverse to do some approximate avalanche simulation. So if you have terrain data, you can create a ton of rocks and just treat them as rigid bodies and drop them and let them, see where they go, that kind of thing. So those sorts of capabilities that come with Omniverse can add a lot to a visualization. That physics simulation capability that I mentioned is even really useful for setting up your scenes. If you want to place things and not have them intersect each other, you can use a physics placement mode that will do the collision detection and prevent them from colliding, that kind of thing. So the sky's kind of the limit for what you can do, but it's also not too hard to at least get started and get some beautiful images out. You just have to switch to, say, like the path tracing renderer, and you're already halfway there. Oh, and one last thing I should mention. You do not have to go through the ParaView connector to get stuff into Omniverse. If you're already working in Jupyter land and you have, say, a mesh data, let's say you have mesh stored in like just a NumPy array, it's fairly easy to get that directly saved in USD, and then you can just load that directly with Omniverse Create. I included a link down at the end, Introduction to USD, that talks about working with USD, and even shows an example working with USD from Jupyter. So I think that covers pretty much everything I had.
Okay, well, thank you very much, Nick. Are there any questions? Any other questions? I see there is a new question from Kumar in the chat. Would Omniverse support volume rendering as well? If so, how do we specify the color transfer function?
So that is a great question. Unfortunately, the answer is not quite yet. Volumes are supported in the ParaView connector, which kind of gives you a hint that volume rendering support is coming to Omniverse. It's just not quite there yet. So in the near future, that's something we hope to add. I know I'm personally interested in doing volume rendering in Omniverse, but I don't think we have a timeline for when it will be available just yet. Ultimately, we expect volume rendering to work through a technology called OpenVDB, and in particular NanoVDB, which is just a format for describing voxel data sets. It's used a lot in film, but it also works just fine for scientific volumes.
All right, well, I have another question. So how do you enable index inside ParaView? Is it just done by switching to volume rendering? It's enabled automatically, or you have to do something else?
Yes, so good question. So for enabling index, once you have the plugin installed, the plugin selected and enabled, then it's just through setting the representation. And like you mentioned, you could set the representation to volume rendering. If you set it to volume, that actually uses ParaView standard volume renderer. So you want to set the representation to NVIDIA index specifically.
Right.